And when I talk about some of these, I mean what we call rational functions. Do you remember what word I told you to think of when you see the word rational? No? We did those rational equations. We did those rational expressions in the last unit. What did they all look like? What's that? Yeah. What else? Yeah. They had variables. Give me an example of a rational one that we did in the last unit. Really? You can't even remember? That's a quadratic equation. All right, I'll wait. When you see the word rational, I told you guys you should be thinking of another word. Look at lesson 5.1. 5.1. 5.1, rational expressions. What do they all look like? Fine, if you don't have that, thank you. Fractions. When you see the word rational, you should be thinking fractions. Okay? We solved rational equations, simple ones back in grade 9. They were fraction equations. We solved more complex ones this year. They were fractions. We simplified by adding and subtracting and multiplying and dividing. And they were all fractions. So what does a rational function look like? It looks like a fraction. So it's a function in the form y equals some function over some other function. It looks like a fraction. Where f of x and g of x are polynomials. What's a polynomial? Polynomial is just an algebraic expression that has numbers, variables, exponents, as long as they're not fractions or negatives. Okay? Or a combination of. It could be a number. 5 is an expression, is a polynomial. 5x is a polynomial. 5x squared is a polynomial. 5x squared plus 2x is a polynomial. Just if whenever you write exponents, you can't have fractions or negative exponents. Okay? And the other thing, and g of x, whatever that is, can never be 0, right? Because we can't divide by 0. So early this year, when we looked at quadratic functions, we started with the most basic one, x squared. And we saw it looked like a parabola. Vertex was at 0, 0, and then we went 1 across, 1 up, 2 across, 4 up, and we got our graph. Okay? What is the most basic rational or fraction function? It would be this one. Just a 1 up top and an x on the bottom. What will this look like if we graph? Well, a lot of times, best way to start when you haven't seen a function before, what its graph looks like, do a table of values. Pick numbers around 0. Pick some negatives, pick some positives. So, if I said x was -4, wouldn't 1 over x be 1 over -4? You just plug that in. Okay. So if x is -4, Oh, sorry, down. My mistake. Should be down here. It's negative 1/4. I did positive 1/4. Should be down. If I plug 2 into this, negative 2 into this, I get 1 over negative 2, or negative a half. So negative 2 is negative a half. Look there. Well, if I plug in negative 1, I get 1 over negative 1, which is just negative 1. So if x is negative 1, y is negative 1. What about if I plug in a half? What's 1 divide negative a half? How do we divide fractions again? Change it to multiplication and do what? Flip the second fraction. So this is the same as 1 times negative 2 over 1, which will work out to negative 2. So if I go negative a half, then I go negative 2. Let's take in a curve shape. You can see. Same reasoning here. Whenever you divide by a fraction, you just multiply by its reciprocal. So if I divide negative 1 over 4, I times negative 4. So I get negative 1/4, negative 4. Okay. What if x was 0? What's y? Well, we don't say it's nothing. No, because we're not solving something. What word do we use? Undefined. No, it is not. So that means it's 0. There's no point on the y-axis. Okay, it's a little weird. What about if x is 1/4? What's 1 divide 1/4? 1 divide 1 over 4 is the same as 1 times, which is? So 1/4 goes up here. Okay, so we skipped across the y-axis and now we went higher. 1 divide a half is 2. 1 divide 1 is 1. 1 divide 2 is just 1/2. And 1 divide 4 is 1/4. So yeah, it mirrors. Okay, so we can sketch this so far. But these aren't the only points. What if I said x was 8? What would y be if x was 8? Plug it in. 1/8, right? Okay, so you notice it keeps getting smaller and smaller and smaller. If x was 1,000,000, what's y going to be? 1 over 1,000,000. Really small. Is it ever going to touch 0? No. It'll always be a really small fraction. So what's going to happen is that it's going to go like this along the x-axis, but never cross it or touch it. Which means it's going to do the same thing in the negatives. It's going to keep going. It's going to keep getting closer and closer to 0, but it'll never reach 0. And it's the same reasoning here. The smaller the fraction, the higher I go. So if I did 1/10, 1 divided 1/10 is 10. I'm never going to get to the y-axis. And here, I'm never going to get to the y-axis. So the graph is two curves. It's two pieces. And what I have to show are the lines where it never touches. So part of your graph, you must include this. Must. Dashed line here, because our curves will never touch. Dashed line here, because our curves will never touch it or cross it. And there's special names for those lines that we'll talk about in a second. But this is what y equals 1 over x looks like. A very different looking graph. Cross out at the bottom, please. Whatever that stuff at the bottom. Don't worry about the name of the shape. But I do want to talk about this stuff. Okay. We saw there was no point on the graph where the x coordinate is 0. When we tried to plug in 0, we got undefined. That means there was a break in the graph at x equals 0, or the y-axis. X equals 0 is also the y-axis. Okay? We call that x equals 0, that dashed line that we drew, that our curves will never touch or cross. The vertical, and this is a new word for you, asymptote. Yeah, just remain calm. At one point, you didn't know what tangent meant, but you learned that. Okay? And what is an asymptote in math? An asymptote is a line that a curve will never touch or cross. You must draw asymptotes as part of your graphs. Yes, on the previous page, the vertical asymptote was the y-axis, but I want you to put a dashed line over that to show me that you know what an asymptote is. Okay? How do we find the asymptotes? Because a lot of times it's not going to be the y-axis. It's whatever makes the denominator undefined, right? So a vertical asymptote occurs whenever we plug in x and we get undefined. That's the same as the non-permissible values. Value or values. There could be more than one. So if I said 1 over x plus 1, what value of x would make the curve undefined? Nope. 1 over x plus 1. What value of x would make the denominator undefined? -1. So that means that x equals -1. That's where your asymptote would go. We'll see that in a second. There's also no point on the graph where the y-coordinate is 0. You cannot, in 1 over x, You cannot plug in some number x so that 1 divide x will give you 0. You can never get 0 as an answer. Okay? Therefore, there's another break in the graph, a horizontal break that we saw on the x-axis. And what's the equation of the x-axis? Y equals 0. That's also an asymptote, but because it's horizontal, why don't we just go ahead and call it the horizontal asymptote? For our purposes, every time we do one of these rational function graphs this year, the horizontal asymptote will always be the x-axis. Okay, always. The vertical will change, or there could be more than one. But for our purposes, the horizontal one will always be y equals 0, which is the same thing as the x-axis. So whenever you graph one of these, you're going to put, yeah, the vertical will change. We'll see in a second. What's the x-intercept? Go back to the graph. Where does it cross the x-axis? Nowhere, so there is none. We could have found that algebraically. How do we find the x-intercept? Don't we make y equals 0? So 0 equals 1 over x. Tell me what number what x could be. 1 divided what is 0? Yeah, there's no such number. I mean, it can't be a positive number. Like if you try 5, 1 divided 5 is 1/5. If you try a negative number, 1 divided -2 is -1/2. It's not 0. If you try 0, 1 divided 0 is undefined. There's no, okay, doesn't exist. Looking at your graph, what's the y-intercept? Again, none. And how could we do that algebraically? Well, plug x equals 0. So the y-intercept is going to be 1 divided by 0, but that's undefined. It also doesn't exist. No. Right, none. Okay, this one's the domain and range. Yeah, remember we use interval notation usually? Actually, interval notation is not good in this case. Yeah, but it's not. It's very simple. Okay, if we did interval notation, x is every number, right? On the graph, except for what? What can't x be? 0. So how do I write, using interval notation, every number except 0? You'd have to write it like this. You would start at -infinity, go up to 0, but not include it. Then you'd have to skip over 0, start at 0 again, but don't include it, and go to +infinity. And how do I unite these two? I put a little u. So that's a little nasty. This is where the other notation is better. X can be everything except for what? So, there. Yes. Inequality notation works better in these ones. It's much simpler. Okay? Interval notation is much more complex. So, for the range, well, it goes down forever, comes up to 0, skips over, and goes up forever. So y can be everything but. So how do I write that? Let's not do this. Good. I would completely avoid the interval notation for this one. Okay. Okay, what happens if we have some other stuff? Like this. This is very simple. All we're doing is we're taking 1 over x and subtracting 3 on the bottom. So we're just adding a negative 3 on the bottom. But it's not going to change the shape. But it will change the asymptotes. So how do you graph these things? How do you graph these things? Okay, let's start with the horizontal asymptote. I said that was going to be the same thing all the time. What did I say it was going to be? What equals 0? Y equals 0. Remember, y equals 0 is horizontal. So I know I'm going to have this. That's for sure. The vertical asymptote. Remember what I said? Right. So what value of x makes the bottom 0? 3. So therefore, the vertical asymptote is x equals 3. So it's not the y-axis, it's over here. It's shifted. Now we know what the shape is going to look like. It's two curves. One of the curves is in the upper right, where the asymptotes cross. One of the curves is in the lower left. But I still need a point for each one. So I do need to do, we're not going to do a very complicated table of values. We're going to do a table of values and we're going to pick a number on either side of 3, because 3 is the asymptote. So I need to pick a number less than 3, and I need to pick a number greater than 3. That will get me a point in each one. Try not to make this too complicated. 2 and 4, excellent. Just go 1 down and 1 up. That's all. So if x is 2, then y is going to be 1 over 2 minus 3, which is what? -1. So 2, -1, there's a point. I know that's a point. And then, don't I just draw it like this? I know what the shape is going to look like. And if x is 4, I get 1 over 4 minus 3. Positive 1. So I get this. And I know the rest of the shape goes like that. Okay. Well, properties. We already said the vertical asymptote was x equals 3. The horizontal asymptote is y equals 0. This one will never change for the ones that we're looking at. Okay. We'll see how they could change next year. We'll worry about that next year. What's the x-intercept? 0? None. It never crosses the x-axis. No, it is not. Yes, well done.
Why though? Because
There is a y-intercept. Now it's hard to see from the graph because it's between 0 and 1. Yes, but I don't know if it's exactly a half. So I got to use algebra. How do we find the y-intercept? Make x equals 0. So y equals 1 over 0 minus 3. What's the y-intercept? Negative 1/3. So if I wanted to be a little bit more precise, I should have moved my curve up a little bit. Okay. What? 3. It's always the vertical asymptote. But remember, this is where we write not equals. X can be, hang on, Chief. X can be everything but 3. This will always be the same. Y can never be 0. Okay, one more we'll look at. 2x plus 4. So again, and I'm going to go a little bit shorthand now, horizontal asymptote. Get that one first. Y equals 0, or the x-axis. Get that one first. Vertical asymptote. Yeah, I got to figure out what value of x makes 2x plus 4 equal to 0. So I got to solve this. Make 2x plus 4 equal to 0. Solve, you get 2x equals negative 4. X equals negative 2. So that's the vertical asymptote. So therefore here. We know there's going to be a curve in the upper right where they cross, the asymptotes cross, and a curve in the lower left. We just got to, I want to see a point on either side. What are you going to pick? What's the vertical asymptote? Right, so I want to pick a number below negative 2 and above negative 2. Negative 3 below. Yes, because they go on forever. So if x is negative 3, I got to do 1 over 2 times negative 3 plus 4. Yeah. 1 over negative 2 or negative a half. So negative 3 is going to be negative a half. And then just finish your curve. And if x is negative 1, then I got to do 2 times negative 1. 1 over 2 times negative 1 plus 4. Maybe you see a pattern developing. Half. If you pick a point 1 on either side, and if you figure out this one, this is going to be the same answer but positive. Because it reflects. 1/2 right there. It's going to look like that. Yeah. So your asymptotes, you just basically have to copy down what we did at the beginning. The vertical is x equals negative 2. The horizontal is y equals 0. They're still not, this is always going to be the same. But for the y-intercept, if you look at your graph, it's going to be a fraction, so I got to use algebra. So I make x equals 0. Therefore, y-intercept is going to be 1 over 2 times 0 plus 4. One quarter. Might as well write that one now. Y can't be 0. Can't be the y-axis. X can't be negative 2. Okay? These are the most basic rational functions. The last thing I want to show you is a couple of others that look slightly different from this. What happens when we throw an x squared into the mix? What does that do to things? So I'm going to show you just sort of 3 special types of those. And then we're going to leave it at that this year for rational functions. So for next week, Monday, yes, Monday, we have class. Definitely exercise 6.4.